252 million years ago, Earth was not a fragile place. It was older than the dinosaurs would ever be. Older than flowering plants. Older even than the familiar shape of the continents. Life had already endured nearly 4 billion years of catastrophe and recovery. Ice ages had come and gone. Supercontinents had assembled and torn themselves apart. Entire lineages had risen, flourished, and vanished without leaving a trace. And yet, by the late Permian period, the planet appeared, by every measure available to life itself, remarkably stable. The continents were fused into a single vast landmass. Pangaea stretched from pole to pole, surrounded by an immense global ocean. With no barriers between landmasses, ecosystems were connected across the planet in a way that would never happen again. Species migrated freely. Climate zones were broad and predictable. Seasons were extreme in the interior, but life had adapted. Forests dominated the land. Not forests we would recognize. No birdsong, no flowers, but dense stands of towering seed ferns, conifers, and ancient trees whose ancestors had survived since before reptiles walked upright. Vast wetlands ringed the coasts. Insects thrived in sizes unimaginable today. Rivers carried nutrients into shallow seas that teemed with life. The oceans, in particular, were rich beyond precedent. Coral reefs, older and structurally different from modern ones, supported complex food webs. Brachiopods, trilobites, ammonoids, and crinoids filled every ecological niche. Sharks and bony fish hunted in abundance. Oxygen levels in the water were sufficient, stable, reliable. For marine life, this was a golden age. On land, the balance was just as firmly established. Reptile-like synapsids ruled the food chain. Some were herbivores the size of cattle, others apex predators with serrated teeth and binocular vision. They hunted across floodplains that had existed for tens of millions of years without interruption. Nothing suggested this dominance was temporary. From a biological perspective, the Permian world looked complete. Evolutionary experiments had stabilized. Food webs were complex but resilient. No single species held absolute control. Extinction, when it occurred, was local, gradual, manageable. Life, it seemed, had learned how to endure. And crucially, there was no sign of impending violence from above. No incoming asteroid, no sudden impact winter. No iridium layer waiting in the future rock record. The sky was quiet. The sun rose and set as it always had. The stars were indifferent. For millions of years, this world persisted with only slow, almost imperceptible change. Global temperatures were warm but not extreme. Carbon dioxide levels were higher than today, yet stable. Sea levels fluctuated gently. The planet breathed in long geological rhythms. If you were a creature living then, extinction would not have felt imminent. It would have felt impossible. The Permian Earth had already survived the worst the universe could throw at it. Asteroid bombardments in deep time. The oxygen crisis that once poisoned nearly all life. Volcanic winters that froze the planet from pole to equator. Compared to those ancient trials, the late Permian was calm. Too calm. Because the danger was not arriving from space. It was rising from below. Far beneath the forests and oceans, deep within the mantle, forces were assembling that life could not perceive and could not adapt to in time. Not a single explosion, not a single moment, but a slow, relentless accumulation of pressure and heat on a scale no ecosystem had ever encountered. The continents above remained unchanged. Rivers flowed, animals hunted, plants photosynthesized beneath a sun that gave no warning. And yet, in hindsight, the signs were already there. Pangaea, for all its advantages, had created a fragile system. One ocean meant one circulatory system for the entire planet. One atmosphere meant any disruption would be global. With fewer shallow continental shelves, the oceans had less capacity to buffer chemical change. The interior of the supercontinent grew increasingly arid, pushing life toward the coasts and concentrating ecosystems into narrower zones. Efficiency had replaced redundancy. The planet had become optimized, but not protected. Still, life adapted as it always had. Species migrated, physiology adjusted. Evolution responded to slow pressures, unaware that the coming change would not be slow at all. What followed would not resemble previous extinctions. There would be no single boundary line, no dramatic instant of darkness. Instead, the world would unravel piece by piece, air first, then water, then land, until survival itself became an exception. The Great Dying did not begin with death. It began with imbalance, a subtle shift in chemistry, a gradual warming, a disruption too small to trigger panic, too large to stop once it began. Life, conditioned by deep time to expect stability or sudden catastrophe, was unprepared for something far more dangerous, a planet changing faster than biology could follow. When extinction finally arrived, it did not strike like a weapon. It crept, and by the time life understood what was happening, there was nowhere left to go. So if nothing struck the Earth, if no asteroid darkened the sky, if no cosmic collision reset the clock, what exactly began the dying? Long before the first forest fell silent, before the oceans began to suffocate, the fate of the Permian world was already being written, slowly, invisibly, by the movement of continents. Over hundreds of millions of years, Earth's surface is never still. Plates drift, collide, weld together, and tear apart again. Most of the time, these motions are background noise to life, but occasionally they reshape the rules of survival themselves. By the late Permian, that reshaping was complete. All major land masses had merged into a single supercontinent, Pangaea. From the frozen south to the arid north, nearly every terrestrial ecosystem on Earth was now part of one continuous world. No oceans separated populations. No distant refuges existed beyond the horizon. Life could walk, or crawl, or migrate across the planet without ever leaving land. At first, this seemed like an evolutionary triumph. Species spread farther than ever before. Competition intensified. Ecosystems grew complex, interdependent, efficient. Predators tracked prey across entire continents. Plants colonized new regions without interruption. Genetic diversity mixed freely. The biosphere became globally integrated in a way never seen before, and never repeated again. But integration has a cost. When continents are separated, extinction is regional. Collapse in one place can be offset by survival in another. Oceans act as buffers, climate systems are compartmentalized. Diversity is preserved through isolation. Pangaea erased that safety net. With one landmass came one climate engine. Atmospheric circulation patterns stretched across hemispheres. Monsoons intensified. Interior regions far from the moderating influence of the sea became brutally seasonal. Scorching hot in summer, bitterly cold in winter. Vast deserts expanded at the heart of the supercontinent, forcing life into narrower, more crowded ecological corridors along the coasts and river systems. This compression mattered. As habitats shrank, ecosystems became denser, more specialized, more finely tuned. Species evolved to fit precise environmental niches, effective but fragile. Redundancy disappeared. If a food source failed, there was no alternative. If a climate zone shifted, there was nowhere equivalent to migrate. The oceans, too, were transformed. Surrounding Pangaea was a single global sea, Panthalassa, larger than all modern oceans combined. With fewer shallow continental shelves, marine life was concentrated into limited coastal zones. These shelves are the engines of ocean productivity, where sunlight, nutrients, and circulation sustain complex food webs. Pangaea reduced their total area dramatically. The deep ocean, meanwhile, became increasingly stagnant. With only one major ocean basin, global circulation slowed. Oxygen-rich surface waters mixed less effectively with the depths. In many regions, deep waters grew oxygen-poor, even hostile to life. Entire layers of the ocean became biologically inaccessible long before extinction struck. Again, life adapted, because it had no choice. Species adjusted their metabolism. Some tolerated lower oxygen, others retreated to shrinking habitable zones. The system held, but only just. Stability was maintained not by resilience, but by balance so precise that even small disturbances could cascade. And disturbances were coming. The assembly of Pangaea did more than reshape climate and ecosystems. It altered the planet's interior dynamics. Continental collisions thickened the crust. Heat built up beneath vast plate interiors. Mantle plumes, columns of superheated rock rising from deep within Earth, had fewer release points at the surface. Pressure accumulated. When continents are fragmented, volcanic activity is dispersed along margins and mid-ocean ridges. When continents unite, that activity can become focused, delayed, and catastrophic when it finally breaks through. None of this was visible at the surface. Forests still stood, rivers still flowed, life still thrived in abundance. But the planet had entered a state that geologists would later recognize as unstable, primed for systemic failure. Pangaea was efficient, too efficient. Energy flowed smoothly through ecosystems, nutrients cycled rapidly. Evolution favored specialization over flexibility. In the short term, this produced dominance and abundance. In the long term, it erased the margins of error that life depends on when conditions change. The planet had optimized itself for a world that no longer existed. When stress arrived, when carbon began to accumulate, when temperatures rose, when oceans lost oxygen, there were no isolated refuges where life could regroup. No distant continents spared the worst effects, no alternative climates waiting beyond the sea. Everything was connected. So when disruption came, it would not spread slowly from place to place. It would arrive everywhere at once. This is the paradox of Pangea. It created the most unified biosphere Earth had ever known, and in doing so ensured that when collapse began, it would be global, synchronized, and devastating. The catastrophe of the late Permian was not triggered by continental assembly, but continental assembly determined how that catastrophe would unfold. It ensured there would be no escape routes, no untouched corners, no second chances, that the world had become singular. One land, one ocean, one atmosphere, one biosphere. And when that single system was pushed beyond its limits, the consequences would be absolute. So the question is not simply what went wrong at the end of the Permian. The deeper question is this: by assembling itself into one perfect interconnected world, had Earth already trapped life in a system too efficient to survive its own success? For tens of millions of years before the end, the land belonged to them, not mammals, not dinosaurs, but creatures that sat somewhere in between, ancient, efficient, and utterly dominant. They were the first true masters of terrestrial Earth, ruling a world that had already forgotten the age of giant insects and amphibians. Among them were the gorgonopsids. They were predators built for certainty, large skulls armed with saber-like canine teeth, forward-facing eyes for depth perception, powerful necks and limbs that lifted their bodies high off the ground, unlike the sprawling reptiles that came before. Their posture allowed speed, endurance, and control. On the Permian plains, nothing hunted them. They were not transitional curiosities. They were apex predators refined by millions of years of evolutionary success. They hunted herbivores the size of modern cattle. They occupied the top of food webs that had stabilized long ago. Generation after generation, their dominance went unchallenged. Earlier still, but no less formidable, were animals like Dimetrodon. Despite popular confusion, Dimetrodon was not a dinosaur, nor even a reptile in the modern sense. It belonged to a lineage closer to mammals than to lizards. Its most striking feature was the great sail rising from its back, a structure of elongated vertebrae covered in skin and blood vessels. This was not decoration, it was physiology, an adaptation for regulating body temperature in a world of extreme seasons. In the cool mornings of the Permian, Dimetrodon could face the sun, warming its blood rapidly. In the heat of midday, it could turn sideways, shedding excess heat. This control gave it a metabolic advantage over competitors, allowing it to hunt when others could not. Its jaws were filled with differentiated teeth, cutting, piercing, tearing. Another mammal-like trait that made it a precision predator. Fish, amphibians, early reptiles, all were prey. Few escaped once targeted. Together, animals like these defined what it meant to rule land. They were not merely large, they were specialized, efficient, perfectly tuned to their environment. Their senses were acute, their hunting strategies refined, their ecosystems stable enough to support generations of top-heavy food chains without collapse. And beneath them, life flourished. Herbivores grazed in enormous numbers. Burrowing animals engineered the soil, insects pollinated seed-bearing plants long before flowers existed. Forests regenerated predictably after fires and floods. Nutrient cycles ran smoothly. There was death, of course, but it was local, expected, absorbed by the system. Extinction, when it happened, was gradual. Species declined slowly, replaced by close relatives. No single event erased entire branches of the tree of life. From an evolutionary standpoint, the Permian world looked solved. These predators had no reason to expect change. They had survived everything Earth had thrown at them so far. Ice ages had come and gone. Sea levels had risen and fallen. Continents had collided with forces that reshaped the planet itself. And through it all, their ancestors endured. Natural selection had taught them a lesson that seemed unbreakable. Adapt, and you will survive. But adaptation has limits. Predators are only as secure as the systems beneath them. They depend on prey, on vegetation, on climate patterns that sustain entire food webs. Remove one layer and the pressure moves upward. Remove several at once, and even the strongest hunters are left with nothing to hunt. The Permian apex predators had evolved for dominance in a stable world, not resilience in a collapsing one. Their bodies were large, their metabolisms demanding. They required abundant oxygen, predictable temperatures, reliable prey populations. They thrived when the world behaved as it always had. They were not built for scarcity, nor were they built for rapid change. Evolution had never tested them against a planet whose chemistry itself was shifting, against air that slowly grew heavier and hotter, against oceans that lost oxygen and began to rot from within, against forests that died not from fire or drought, but from invisible stress. There was no instinct that warned them. No predator could sense carbon dioxide accumulating in the atmosphere. No behavioral adaptation could counter ultraviolet radiation creeping through a thinning sky. No hunting strategy could compensate for ecosystems unraveling everywhere at once. When stress began to mount, it would not announce itself with sudden catastrophe. It would begin subtly, prey growing smaller, migration shifting, breeding cycles faltering. The kind of changes that ecosystems had absorbed before. At first, the great predators likely survived. But dominance is not immunity. As plant communities faltered, herbivores declined. As herbivores vanished, predators followed. Large bodies became liabilities. High energy demands became death sentences. The very traits that had made these animals supreme now worked against them. They had no evolutionary memory of a world this unstable. And so the masters of Earth, unchallenged for millions of years, faced something no claw or tooth could confront. Not a rival, not a catastrophe they could flee, but a planetary transformation that did not care who stood at the top, which raises the question that hangs over their extinction like a shadow. What force could possibly threaten creatures that had no natural enemies at all? The first sign that something was wrong did not appear in the sky. It did not come as earthquakes that shattered forests, nor as explosions that darkened the sun. Life on the surface noticed nothing at all. The world above continued as it always had, unaware that far below the planet's interior was entering one of the most violent phases in its history. Beneath what is now northern Asia, the Earth's mantle began to surge. This was not an ordinary volcanic event. It was the slow arrival of a mantle plume, a massive upwelling of superheated rock rising from near the boundary between Earth's core and mantle. These plumes move on geological timescales, building pressure over millions of years. And when they finally reach the crust, they do not erupt politely. They tear the planet open, and what emerged was the Siberian Traps, one of the largest volcanic provinces ever known. Not a mountain, not a chain of volcanoes, but a continental-scale wound. Millions of square kilometers of crust fractured and flooded with lava again and again. This was not a single catastrophe. It was a prolonged assault. For hundreds of thousands, possibly over 1 million years, magma poured out through fissures that stretched for kilometers. Lava did not explode skyward in brief violence. It flowed outward in vast sheets, spreading across the land like an advancing ocean of fire. Each eruption buried the previous one, then another followed, and another. Layer upon layer accumulated, eventually forming basalt stacks several kilometers thick. If a human had stood there, had that been possible, they would not have seen towering cones or dramatic plumes at first. They would have seen the ground split open, glowing red, and rivers of molten rock advancing relentlessly, consuming everything in their path. But the true danger was not the lava. It was the gas. As magma rose, it released enormous quantities of carbon dioxide, sulfur dioxide, and halogens, chlorine and fluorine compounds capable of destroying ozone. Trillions of tons of greenhouse gases entered the atmosphere, not in a single pulse but in repeated waves that prevented the climate from ever stabilizing. And it did not stop there. The Siberian Traps erupted through some of the worst possible rock on Earth. Beneath the surface lay vast deposits of coal, oil-rich sediments, and evaporates. As magma intruded into these layers, it baked them, burned them, vaporized them. This contact metamorphism released additional carbon dioxide and methane, far more potent greenhouse gases than volcanism alone could produce. It was not just Earth's interior speaking. It was Earth's ancient carbon stores being forcibly returned to the atmosphere. In effect, the planet was exhaling everything it had buried over hundreds of millions of years. The rate mattered. Volcanoes had erupted before. Far larger explosions had occurred in deep time, but most were brief, separated by long recovery periods. Life could adapt. Ecosystems could migrate. Carbon cycles could rebalance. This time, the input never stopped. Each eruption arrived before the effects of the last had faded. Temperatures rose, then rose again. Oceans absorbed carbon, then more carbon until their chemistry began to fail. The atmosphere thickened, heat accumulated, feedback loops began to take control, and the planet crossed thresholds it had never crossed before. Sulfur dioxide initially caused short-term cooling, forming reflective aerosols in the atmosphere. But this effect was temporary. Carbon dioxide persisted. Methane amplified warming. Over time, the cooling pulses gave way to relentless heat. Global temperatures climbed by several degrees, then more. The poles warmed dramatically, ice vanished, sea levels fluctuated erratically. On land, evaporation intensified, drying soils and stressing plant life. In the oceans, warm water held less oxygen. Circulation slowed, dead zones expanded, still the eruptions continued. What made the Siberian Traps uniquely lethal was not just their scale, but their timing and duration. They unfolded at the worst possible moment, when Earth's biosphere was unified, specialized, and vulnerable. There were no isolated continents to act as sanctuaries, no independent oceans to preserve stable chemistry. Everything shared the same air, everything shared the same water, and all of it was being poisoned at once. There's evidence that volcanic gases also damaged the ozone layer, thinning the planet's protective shield against ultraviolet radiation. With less ozone, UV light scorched the surface, damaging plant tissues, disrupting reproduction, and sterilizing shallow waters where much marine life reproduced. Life was now under assault from above and below simultaneously. And yet, extinction did not happen overnight. At first, ecosystems strained but endured. Species distributions shifted. Some organisms adapted to heat and low oxygen. But adaptation requires time, and the Siberian traps did not grant it. The planet was being forced into a new state faster than evolution could respond. This is the critical distinction. The Great Dying was not caused by volcanism alone. It was caused by sustained, cumulative disruption, a geological siege that overwhelmed Earth's regulatory systems. Carbon cycles failed, climate stabilization failed, oxygen balance failed. The planet entered a runaway condition. By the time the eruptions finally waned, the damage was irreversible. The atmosphere had changed, the oceans had changed, the biosphere had crossed a line from which it could not quickly return. Volcanoes had erupted before, but never like this, never for this long, never against a planet so interconnected, so finely balanced, so utterly unprepared. So the question remains hanging over the ruins of a world. If Earth had survived countless eruptions before, why did this one succeed in nearly ending life itself? At first, nothing looked like an ending. There was no single year when the sky darkened permanently, no moment when the sun failed to rise. What began instead was a subtle change, one that would have gone unnoticed to any creature living through it. Seasons still turned, forests still grew, predators still hunted. But the air itself was slowly becoming something unfamiliar. The process did not start in the atmosphere. It started with accumulation. With each new phase of volcanic activity, invisible gases seeped upward and spread across the planet. Carbon dioxide did not behave like ash or smoke. It did not fall back to the ground. It lingered. It mixed. It stayed. Year after year, century after century, the concentration rose, not in dramatic spikes, but in a steady, relentless climb. At first, the planet absorbed it. Oceans took in carbon, just as they always had. Forests continued to photosynthesize. Weather systems redistributed heat. Earth's natural regulators, chemical, biological, geological, worked as they had for hundreds of millions of years. But they were never designed for this pace. Carbon dioxide is not merely a gas. It is a thermal trap. It allows sunlight to reach the surface, but it slows the escape of heat back into space. With every incremental increase, a little more warmth remained behind. A fraction of a degree here, another fraction there. The warming was uneven. The tropics, already hot, became oppressive. But it was the higher latitudes that changed most dramatically. Polar regions warmed faster than the rest of the planet. Seasonal ice diminished, snow cover retreated. Surfaces that once reflected sunlight now absorbed it, amplifying the heat. This was the first feedback loop to awaken. As ice vanished, warming accelerated. As warming accelerated, more ice vanished. Earth's climate system began to reinforce its own imbalance. Weather patterns shifted. Rainfall became erratic. Some regions grew wetter, others drier. Monsoon systems intensified, then destabilized. Floods scoured landscapes that had once supported stable forests. Elsewhere, prolonged drought weakened plant life, making ecosystems brittle and vulnerable. Plants struggled not because it was warm, but because it was changing too quickly. Photosynthesis depends on predictable conditions. Temperature, moisture, and sunlight must align within tolerable ranges. As heat increased and rainfall patterns fractured, forests lost their ability to regulate the atmosphere. Carbon uptake slowed. More carbon remained airborne. Another feedback loop closed. The atmosphere thickened, not physically but energetically. Heat waves became longer. Nights no longer cooled as efficiently. Soil moisture evaporated faster than it could be replenished. Fires became more frequent, releasing even more carbon from biomass back into the air. The planet was beginning to warm itself. Meanwhile, the oceans, the largest heat sink on Earth, absorbed vast amounts of excess energy. Surface waters grew warmer, expanding and becoming lighter. This disrupted vertical mixing. Oxygen-rich surface water no longer sank as efficiently into the depths. Deep oceans began to suffocate. Warm water holds less oxygen than cold water. As temperatures rose, marine habitats shrank vertically. Species that required well-oxygenated water were squeezed into thinner surface layers, competing for dwindling resources. Below them, vast zones became stagnant and hostile. But the warming did not stop. As oceans heated, they released dissolved gases. Carbon dioxide seeped back into the atmosphere, weakening the ocean's role as a buffer. Methane, trapped in sediments and biological processes, began to escape in small but increasing amounts, adding another potent greenhouse gas to the mix. The system was no longer linear. Each degree of warming made the next easier. On land, heat stress disrupted reproduction cycles. Seeds failed more often, insects hatched out of sync with plants, herbivores found less nutritious food, predators followed, not yet extinct but increasingly strained. Still, there was no single catastrophe. This is what made the transition so dangerous. Life had evolved to survive shocks, asteroids, eruptions, sudden freezes. But this was not a shock, it was a slope. A gradual incline that led toward a cliff no one could see from the bottom. At some point, Earth crossed a threshold. The exact moment is lost to time, but the consequences are not. Beyond that line, natural cooling mechanisms could no longer counteract warming. Even if volcanic emissions had ceased instantly, the feedbacks already in motion would have continued. Ice loss, reduced reflectivity, ocean stratification, carbon release, heat retention. The planet had entered a new state. Temperatures climbed several degrees above previous norms, not briefly, not locally, globally. The difference between a stable world and an unstable one is not measured in tens of degrees, but in small shifts that cascade through every system at once. Life began to experience conditions it had never encountered in its long history. The poles resembled temperate zones. Temperate zones verged on subtropical heat. Interior regions became punishingly hot and dry. Night offered little relief. Daylight intensified stress on already weakened organisms. The sky itself had become an adversary, and yet from the perspective of an individual creature, extinction still did not feel inevitable. Animals lived their lifespans unaware that the world they depended on was slipping away beneath them. Forests still stood even as their growth slowed. Oceans still teemed even as oxygen declined. The trap lay in delay. Climate systems respond slowly, but once set in motion, they are difficult to stop. By the time the full consequences of warming became unavoidable, the forces driving it were no longer external, they were internal. Earth was now warming because it had learned how to warm itself. Which leads to the most unsettling question of all. If this much warming could unravel an entire living world, how much is too much for a planet to survive? For a time, the oceans did what they had always done. They absorbed the excess. Water is patient. It takes in heat, it takes in carbon, it buffers extremes and smooths violence. For hundreds of millions of years, this quiet service had kept Earth livable, even during upheaval. And as the atmosphere thickened and warmed, the seas once again became the planet's shield. But every shield has a limit. As carbon dioxide accumulated overhead, it dissolved into the surface waters. Molecule by molecule, the chemistry of the oceans began to change. Carbon dioxide reacts with seawater to form carbonic acid, lowering the pH. At first, the shift was slight, imperceptible to anything without instruments. Then it continued. And continued. The oceans were not becoming acidic in the way of a burning chemical bath. They were becoming subtly, relentlessly corrosive. The balance that marine life depended on, maintained for eons, was slipping. For creatures that built their bodies from calcium carbonate, this change was existential. Shells, skeletons, reefs, all rely on a delicate chemical equilibrium. As acidity increased, forming and maintaining these structures became harder. Then energetically expensive. Then, in some regions, impossible. Juvenile organisms struggled first. Larvae failed to form proper shells. Growth slowed. Survival rates fell. Species that had thrived for tens of millions of years began to thin, not suddenly but steadily. Reefs were among the earliest casualties. These ancient structures were not just habitats. They were the foundation of marine ecosystems. Reefs sheltered nurseries, concentrated food, and stabilized coastlines. As they weakened, entire food webs unraveled with them. The oceans lost complexity. At the same time, warming continued to erode oxygen levels. Warm surface waters resisted mixing with cooler depths. Stratification intensified. Below the sunlit layers, oxygen was consumed by bacteria and not replenished. Dead zones expanded. In these suffocating waters, only specialized microbes could survive. They thrived on decay, breaking down sinking organic matter. But their metabolism produced hydrogen sulfide, a toxic gas lethal to most complex life. In places, the ocean quite literally began to rot. These anoxic sulfidic waters spread outward and upward. Fish fled when they could. Sessile organisms died where they stood. Entire seafloors became biological deserts, and the poison did not always stay below. Hydrogen sulfide can escape into the atmosphere. When it does, it attacks the ozone layer and poisons air-breathing life. Evidence suggests this happened repeatedly, bursts of toxicity rising from the seas, compounding the stress already imposed by heat and ultraviolet radiation. The ocean was no longer just failing. It was turning hostile. Food chains collapsed from the bottom up. Plankton communities shifted toward species better adapted to low oxygen and high acidity, but less capable of supporting higher life. Larger organisms starved even where temperatures remained tolerable. Predators found empty waters. The loss was not evenly distributed. Some regions died faster than others. Shallow seas near the coasts suffered first. Then deeper environments followed. What made this extinction unprecedented was its breadth. Few marine refuges remained untouched. Life attempted to adapt. Some species reduced their size, lowering oxygen demand. Others altered their metabolism. But these changes required generations, and the environment continued to degrade faster than evolution could respond. The sea had once been life's cradle. Now it was a narrowing corridor closing from all sides. As marine productivity declined, the consequences did not remain at sea. Oceans are not separate from land. They regulate climate, recycle nutrients, and drive weather systems. As biological activity faltered, these functions weakened. Carbon burial slowed. More greenhouse gases remained in circulation. Warming accelerated further. Another feedback loop locked into place. Meanwhile, coastal ecosystems, estuaries, wetlands, shallow shelves, collapsed. These regions had buffered storms, filtered water, and supported vast populations of organisms. Their loss made shorelines unstable and nutrient cycles erratic. On land, the effects were already being felt. Weather became more extreme as ocean-atmosphere interactions destabilized. Rainfall patterns grew unpredictable. Soils eroded. Rivers alternated between flood and drought. Terrestrial plants, already stressed by heat, now faced nutrient imbalances and disrupted hydrology. The failure of the seas was reaching inland, and still extinction advanced in waves rather than a single blow. Species vanished regionally, then globally. Diversity plummeted. Ecological roles went unfilled. Systems that had once absorbed loss now amplified it. By the end, the oceans would lose nearly all complex life. 96% of marine species would disappear, not because the seas boiled, not because they froze, but because the chemistry that made them habitable quietly slipped out of range. The most chilling aspect of this collapse is its orderliness. There was no chaos at first, no sudden crash, just a steady narrowing of possibility until survival became mathematically improbable. The ocean did not rage against life, it simply stopped supporting it. And as the seas fell silent, a far more dangerous question emerged, one the planet itself would soon be forced to answer. If the oceans die, can life on land survive at all? Long before the surface world understood what was happening, the most dangerous phase of the crisis was already waiting in silence. It lay buried beneath the oceans. Along the continental margins, locked within cold sediments under immense pressure, existed a vast and unstable reservoir of carbon, methane hydrates. Ice-like crystalline structures trapping methane gas had accumulated there for millions of years. They formed slowly, molecule by molecule, under conditions so specific that they acted like a geological vault, stable, inert, harmless. As long as the ocean stayed cold, as long as pressure remained constant, as long as the planet did not change too quickly. But the planet was changing. As global temperatures rose, the oceans absorbed heat. Surface waters warmed first, then gradually transmitted that warmth downward. At the same time, sea levels fluctuated as ice disappeared and thermal expansion altered pressure along the seafloor. The balance that kept methane locked away began to weaken. Hydrates do not explode all at once. They destabilize. At first, small amounts of methane escaped. Bubbles rose through the water column and dissolved before reaching the surface. The gas oxidized, becoming carbon dioxide, a minor contribution. Another burden added to an already overloaded system. But warming did not pause. As temperatures climbed further, entire fields of hydrates crossed their stability threshold. The crystalline cages holding methane broke apart. Gas escaped faster than microbes could consume it. Plumes rose from the seabed in quantities unseen in Earth's history. Methane entered the ocean, and then the atmosphere. Methane is not a subtle gas. Over short timescales, it traps heat far more efficiently than carbon dioxide. Even small increases have outsized effects. When it reached the air, it accelerated warming dramatically, adding fuel to a climate already burning out of control. This was the moment the system changed character. Until now, warming had been driven primarily by external forcing, volcanism, carbon release, disrupted cycles. But with methane in play, the planet acquired a new ability, It could amplify itself. Warming released methane. Methane caused more warming. More warming destabilized more hydrates. The loop closed. This feedback did not require new eruptions. It did not depend on tectonics or chance. It fed on temperature alone. Once initiated, it became increasingly difficult to stop. The oceans responded violently. As methane rose through the water, it stripped oxygen from surrounding layers during oxidation. Anoxic zones expanded rapidly. Hydrogen sulfide production intensified. Entire regions became chemically hostile within years to decades, an instant in geological time. Marine life faced an impossible choice. Flee upward into warmer, oxygen-poor surface waters or remain below and suffocate. Many did neither. They died where they were. Methane plumes may also have reached the surface in bursts, entering the atmosphere directly. When this happened, the climate response was abrupt. Temperature spikes followed. Weather systems destabilized further. Rainfall patterns shifted again, becoming more extreme, more erratic. On land, ecosystems already near their limits were pushed beyond them. Heat waves grew longer. Nighttime temperatures remained elevated, offering no recovery. Plants closed their stomata to conserve water, reducing carbon uptake. Photosynthesis slowed. Growth stalled. Forests began to thin. Soils dried and cracked. Microbial activity changed, releasing additional greenhouse gases. Fires became more common, not as isolated events, but as recurring features of the landscape. Each fire returned ancient carbon to the air, another loop. What made this phase uniquely devastating was speed. Evolution can handle gradual change. It can even recover from sudden shocks if enough niches remain intact. But runaway feedbacks erase the middle ground. Conditions deteriorate everywhere, all at once, faster than adaptation could track. Life found itself chasing a moving target that accelerated away. The warming also altered atmospheric circulation. Heat gradients between equator and poles weakened, disrupting jet streams and global wind patterns. Weather stagnated in some regions and intensified in others. Droughts lingered, storms stalled, extremes replaced averages, that the climate lost its memory. Meanwhile, methane itself began to break down under ultraviolet radiation, eventually converting to carbon dioxide. But this did not solve the problem. It merely transformed a short-lived accelerant into a long-lived burden. Heat remained trapped. Warming persisted. The planet had entered what scientists would later describe as a hothouse state, and crucially, there was no off switch. Even if volcanic emissions had ceased entirely at this moment, the feedbacks already unleashed would have continued to drive warming for thousands of years. Ice loss, albedo reduction, ocean stratification, methane release, all were now internal drivers. Earth was no longer responding, it was acting. The biosphere felt the consequences immediately. Reproduction failed across multiple lineages. Temperature-sensitive processes, egg development, seed germination, larval survival, collapsed. Food webs fractured at multiple points simultaneously. Recovery in one region was negated by collapse in another. This was not selective extinction. This was systemic failure. Large animals suffered first. High oxygen demand, large body mass, and long generation times made adaptation impossible. Apex predators vanished as prey disappeared. Herbivores followed as plant communities collapsed. Smaller organisms lingered longer, but even they faced narrowing margins. Heat, acidity, toxicity, and oxygen loss converged from every direction. The planet had become a machine optimized for stress. And yet, extinction was still unfolding. Not complete, not instantaneous. Life clung to existence in pockets. Some microbes thrived. Some opportunistic species expanded briefly into emptied niches. But the trend was unmistakable. Each century brought fewer species. Each millennium reduced complexity further. The biosphere was simplifying, not because life wanted to, but because complexity had become unsustainable. At this stage, the question of prevention becomes meaningless. The forces driving extinction were no longer external threats that could be removed. They were intrinsic properties of the altered planet. Earth's climate system had crossed into a regime where its own physics ensured continued deterioration. The Great Dying did not happen because life was weak. It happened because the environment became hostile faster than life could adapt, and as methane continued to escape, as heat continued to build, as oceans continued to suffocate, the final question loomed, unavoidable, unsettling, and still debated. Once the planet began to warm itself, was extinction no longer a possibility, but an inevitability? What do you think about this whole process? Share your thoughts in the comments section. The sky had always been life's silent ally. Invisible, vast, taken for granted, it filtered the sun's violence into something tolerable. For hundreds of millions of years, a thin veil of ozone high in the atmosphere absorbed the most dangerous wavelengths of ultraviolet radiation, protecting DNA, stabilizing ecosystems, allowing complex life to exist on land at all. And then, quietly, that protection began to fail. The damage did not come from a single source. It emerged from convergence. Volcanic gases rich in chlorine and fluorine rose into the stratosphere. Hydrogen sulfide released from anoxic oceans followed, breaking down under sunlight into compounds that attacked ozone molecules. Methane oxidation altered atmospheric chemistry further, changing reaction rates in ways that favored destruction over repair. Ozone is constantly formed and destroyed in a delicate balance. What changed during the late Permian was not the process, but the scale. Destruction began to outpace regeneration. At first, thinning was regional, subtle, seasonal. Ultraviolet levels increased slightly, enough to stress organisms, not enough to sterilize landscapes. Plants responded defensively. Leaves thickened, growth slowed, reproduction became less reliable. But the assault continued. As ozone concentrations dropped further, ultraviolet radiation intensified. DNA damage increased. Cells mutated faster than repair mechanisms could correct. Spores and pollen, especially vulnerable to UV, failed in greater numbers. Seed viability declined. Forests did not collapse all at once. They died standing. Trees that had grown for decades, even centuries, remained upright as their ability to reproduce vanished. New growth failed to replace the old. Canopies thinned, gaps opened. Sunlight reached the forest floor with lethal intensity. What replaced trees was not another forest. It was fungi. The fossil record preserves this moment with chilling clarity. Spores appear in overwhelming abundance, far beyond normal levels. This fungal spike marks a world where plant matter accumulated faster than ecosystems could recycle it, and where decomposers briefly dominated landscapes stripped of higher life. Fungi thrive where systems have failed. They do not need stability, they feed on death. As forests collapsed, soils lost their anchors. Erosion accelerated, nutrients washed into rivers, then into already stressed oceans, worsening anoxia and toxicity. The boundaries between land and sea blurred into zones of decay. Daylight became dangerous. Ultraviolet radiation penetrated deeper into the water column, sterilizing surface layers where plankton once flourished. Photosynthetic organisms, already stressed by heat and acidity, were exposed to radiation levels they had never evolved to tolerate. Primary productivity collapsed. Without plankton, marine food webs disintegrated from the base upward. The few organisms that survived retreated deeper, but deeper waters lacked oxygen. The sea offered no refuge. On land, animals altered their behavior. Burrowing increased. Nocturnality may have offered temporary relief, but these were stopgap measures, not solutions. UV damage accumulated across lifespans. Fertility declined. Developmental abnormalities increased. Survival in open environments became nearly impossible. This was the ordeal, not a single catastrophe, but a convergence of failures that removed the last remaining margins of safety. Heat stressed physiology. Oxygen loss suffocated tissues. Toxic gases poisoned air and water, and now radiation attacked life at the molecular level. The planet was no longer merely hostile. It was actively destructive. The most vulnerable species vanished first. Amphibians, already sensitive to environmental change, declined rapidly. Large herbivores followed as vegetation disappeared. Apex predators, deprived of prey and exposed to cumulative stress, collapsed soon after. But even microbes were affected. Ultraviolet radiation penetrated shallow soils and surface waters, damaging bacterial communities that drove nutrient cycling. With decomposers impaired and primary producers failing, ecosystems lost their ability to regenerate themselves. This is the point at which Earth came closest to total biological failure. Not extinction of all life, but extinction of complexity. The biosphere was reduced toward its simplest components: heat-tolerant microbes, fungi, and a handful of opportunistic survivors. Multicellular ecosystems, the intricate webs that had taken hundreds of millions of years to assemble, were unraveling everywhere at once. There were no refuges left on the surface, no forest canopies thick enough to block radiation, no shallow seas safe enough for reproduction, no climate zones stable enough to support long-lived communities. Life retreated into shadows, sediments, and burrows, anywhere the sky could not reach, and still, the planet offered no reprieve. This was not a temporary ozone fluctuation that could heal in decades. The chemical assaults continued. The atmosphere remained unstable. Each recovery attempt was undercut by renewed stress. The Great Dying did not peak with fire or flood. It peaked with exposure. with a sun that had not grown brighter shining through a sky that could no longer protect the world beneath it. By this stage, extinction was no longer a future event. It was underway. Species were disappearing faster than they could be named. Entire lineages collapsed without leaving descendants. Ecosystems that had persisted since before reptiles existed were erased in what amounted to a geological instant, which leads to the most haunting question of all. By the time the sky failed completely, how much life was already gone? The Permian Earth, just before the extinction, had been a world of astonishing complexity. Every niche, from the shallow reefs to the deepest forests, had been filled. Oceans pulsed with life, rivers teemed with amphibians, swamps hummed with insects, and land was ruled by the most sophisticated predators the planet had ever produced. Yet as the planet's climate unraveled, this intricate web of life began to snap, strand by strand. The first victims were the ocean's architects. Reef-building organisms, long-standing builders of underwater landscapes, were among the earliest to falter. Rugose and tabulate corals, lineages that had persisted for hundreds of millions of years, began to dissolve in increasingly acidic waters. Their calcium carbonate skeletons, normally stable, could no longer form. Algae that lived symbiotically within these corals failed to photosynthesize under the rising temperature and ultraviolet stress. Together, coral and algae collapsed. Reefs, the bustling metropolises of the Permian seas, fell silent. Sheltered niches disappeared, and with them the myriad species that relied on them. Alongside corals, brachiopods, the armored filter feeders that carpeted the seafloor, succumbed in astonishing numbers. Spiriferids, with their folded shells, and productids, the flat, spiny forms, were widespread across shallow marine shelves. As oxygen declined and oceans became increasingly acidic, their shells weakened. Unable to feed effectively, they died en masse, leaving entire seafloors blank, barren, and silent. Bivalves fared only slightly better. Some lineages persisted, but most were local extinctions. Trilobites, survivors of previous mass extinctions for more than 270 million years, vanished completely. Once ubiquitous on the shallow seabed, their complex exoskeletons required precise conditions for molting and development. As the oceans warmed and acidified, these conditions failed, and their extinction was one of the most poignant indicators that even the most resilient lineages were not immune. The collapse continued upward through the food web. Crinoids, stalked echinoderms that resembled underwater flowers, slowly disappeared as oxygen levels in deeper waters dropped. Gastropods and other mollusks followed, particularly species dependent on coral reefs for shelter and food. Predatory fish, unable to find sufficient prey, starved in a cascading effect that left the upper levels of the food web barren. Amid these losses, certain opportunistic organisms momentarily surged. Microbes that could tolerate low oxygen, extreme heat, and chemical toxicity proliferated. Cyanobacteria and sulfide-tolerant bacteria dominated nearshore environments, creating conditions inhospitable to complex multicellular life. Yet their dominance was a grim echo of life's former abundance, not a restoration. On land, the sequence of collapse followed a similar but uniquely devastating pattern. Forests, once lush and stable, began to thin under combined stresses: heat, drought, acid rain, and ultraviolet radiation penetrating the weakened ozone layer. Glossopteris, the long-lived seed ferns that formed vast swampy forests across Gondwana, declined sharply. These plants had dominated terrestrial landscapes for tens of millions of years, forming the backbone of terrestrial ecosystems. As they died, the herbivores that fed upon them, the ancestors of later dicynodonts and small synapsids, lost their primary food source. Large herbivorous synapsids such as pariasaurs and the lumbering dicynodonts struggled next. These animals, some reaching the size of modern cattle, required abundant vegetation to sustain their metabolism. With swamps drying and forests dying, food became scarce. Migration offered little relief because the destruction was near global. Populations dwindled, leaving skeletal remains that would fossilize for hundreds of millions of years. As evidence of the dying, carnivorous synapsids, the gorgonopsids that had ruled the land for millions of years, followed swiftly. These apex predators, with their saber-like teeth and powerful build, were dependent on prey abundance. As herbivores disappeared, starvation combined with heat stress and ultraviolet exposure decimated their populations. By the end of the crisis, the gorgonopsids were gone, leaving no comparable land predators to fill the ecological vacuum for tens of millions of years. Amphibians, too, suffered catastrophic losses. Temnospondylus, which had diversified in swampy environments and rivers, faced multiple simultaneous stresses: drying habitats, acidic waters, and ozone-driven ultraviolet radiation. Their permeable skin, once an asset for cutaneous respiration, became a liability. Populations collapsed in local extinctions that aggregated into global disappearance. Insects were not spared. Early Permian lineages of giant cockroaches, dragonflies, and millipedes, already adapted to specific humidity and temperature regimes, declined rapidly. The loss of forests destroyed their habitats, leaving many species with nowhere to reproduce. Pollination networks collapsed, creating a feedback loop that further weakened plant reproduction. The microscopic and the massive were both under siege. The seas and land dying in tandem converged to create one of the most complete mass extinctions in Earth's history. Extinction was not a momentary event, but a series of cascading failures. By the end, estimates suggest 96% of marine species were gone, and 70% of terrestrial vertebrates had disappeared. Ecosystems that had persisted since the early Paleozoic, the Devonian reefs, the Carboniferous forests, were now largely erased. The biosphere had been reduced to an almost skeletal form. What remained were small, generalized survivors. Certain burrowing reptiles and synapsids, such as Lystrosaurus, endured. They were small, hardy, and able to subsist on marginal food sources. Heat-tolerant plants with short lifespans and rapid reproduction, early ferns and seed ferns, clung to survival. Microbial communities and fungi filled niches vacated by complex plants and animals, thriving in conditions that were otherwise lethal. The fungal spike that appears in the fossil record reflects this surge of decomposers, feeding on dead wood, fallen leaves, and decaying carcasses. The oceans, while nearly devoid of fish and invertebrates, contained microbial survivors. Certain small crustaceans and opportunistic bivalves persisted in oxygenated refuges or in deeper, cooler waters. Yet for the majority of species, the world was unrecognizable. Life's diversity had been reduced to a fraction of its former self, ecosystems simplified to the most fundamental interactions. The environmental sequence that led to this annihilation reveals a cruel order. First, chemical stress, acidification, and oxygen depletion killed the most sensitive marine organisms. Next, herbivores on land declined as vegetation failed. Apex predators starved, amplifying the effect. Insects and other specialized species collapsed alongside their plants. Microbial life temporarily dominated, but the chemical and thermal stresses of the ocean and atmosphere continued to increase. Finally, ultraviolet radiation reached its peak, finishing the decimation of any remaining surface-adapted species. It was an extinction without mercy, without hierarchy, without partial reprieve. Evolutionary resilience, which had carried life through ice ages, asteroid strikes, and other volcanic events, failed here because the planet itself had become the threat. Every system, atmosphere, ocean, land, was hostile simultaneously. Survival became a matter of size, flexibility, and fortuitous location. In this dead world, the most vivid indicators of loss are fossilized in rock. Layer upon layer of sediment records the disappearance of once thriving ecosystems. Coral rubble, brachiopod shells, and trilobite exoskeletons vanish abruptly. Fossilized trees show stress rings, spore layers dominate, and the remains of synapsids and amphibians thin to occasional scattered examples. The sequence is unmistakable. Extinction unfolded in a wave moving through the marine, freshwater, and terrestrial realms. By the end, the planet had entered a liminal state. Life existed, but only just. Complexity had been stripped from ecosystems. Food webs were fractured. Many ecological niches were empty. The Earth had become a canvas of emptiness punctuated by a few scattered survivors, the threads from which new ecosystems could eventually emerge. Yet even in this near-total annihilation, recovery was not immediate. The Great Dying left a world where climate remained unstable, oceans were still toxic, and ultraviolet radiation continued to scour the land. For millions of years, the biosphere remained fragile, populated by resilient but low-diversity organisms. Lystrosaurus and other small survivors dominated terrestrial landscapes. In the oceans, microbial mats and opportunistic bivalves were the primary inhabitants. Forests and reefs would not re-establish for tens of millions of years. The scale of this event dwarfs nearly every other extinction in Earth's history. Unlike asteroid-driven extinctions which struck suddenly, the Permian Triassic event unfolded over tens to hundreds of thousands of years. Yet the result was arguably more catastrophic. Nearly all ecosystems were affected, and the recovery of complexity took 10 million years, a geological eternity. And as the dust settled on this emptied world, the question emerges, heavy and unresolved: what does a dead planet look like? Not merely a place without life, but a place stripped of complexity, where the architecture of ecosystems itself has been erased, leaving silence, fungal mats, and the faint, stubborn pulse of a few survivors. It is a world that whispers of both mortality and resilience, and a warning of how fragile even the most dominant life can be when the planet itself turns against it. The world after the Great Dying was a silence unlike any before. Forests no longer dominated the land. The towering glossopterids, seed ferns, and giant lycophytes that had filled the Permian continents were gone. Their absence left a landscape of bare soil, eroding slopes, and sporadic shrubs. Rivers ran hotter, muddier, more acidic. Coastal plains, stripped of vegetation, shifted with each storm. Winds scoured sediment that once held the footprints of thriving animals, erasing the last traces of life's former grandeur. Into this void came the fungi. They did not arrive as a surprise. They had always existed as decomposers, recyclers of life's detritus. But now, with so much organic material from dead forests, decaying plants, and the carcasses of terrestrial vertebrates, they became dominant. Spore clouds filled the air. Thick mats of mycelium crept across soil, feeding on anything left, breaking down cellulose and lignin with ruthless efficiency. Fossil layers from this time reveal a spike in fungal spores so dramatic that it dominates the record, a signal of a biosphere stripped to its most basic recycling machinery. For millions of years, this fungal dominance defined the land. Herbivores that survived were few, small, and often burrowed to avoid heat and radiation. Apex predators were nearly absent. Without trees and large plants, the vertical structure of ecosystems collapsed. The world became flat, dominated by low-lying vegetation and fungal carpets. The coal gap tells the same story. In the Carboniferous and Permian, vast swamps of decaying plant matter had compressed over millions of years to form rich coal beds. After the Great Dying, these swamps disappeared. No new coal formed for millions of years. Without forests to supply continuous plant material, without stable wetland ecosystems to compress it, Earth experienced a geological pause in its carbon sequestration. The absence of coal is a marker of how deeply life had been interrupted, how the processes that had built ecosystems and shaped the atmosphere had stalled. Oceans remained hostile. Acidified waters continued to limit biodiversity. Oxygen levels in deeper layers were still dangerously low. Shallow seas saw blooms of microbial life and small, opportunistic bivalves. But the complex coral reefs, sponges, and brachiopod assemblages that had defined the Permian were gone. Food webs remained truncated. The surviving organisms were often simple, hardy, and capable of tolerating extremes, but none could restore the richness of what had been lost. Life had not stopped entirely, but evolution itself slowed. With most niches empty, selective pressures were uneven. Opportunistic species dominated by default, not because they were superior. New forms appeared cautiously, tentatively, and often failed to establish. For millions of years, the world was governed by survival at the most basic level: feeding, reproducing, enduring heat and chemical stress. Innovation, radiation into new forms and complexity, was almost entirely paused. Even the land-dwelling survivors were constrained by the ongoing instability of the climate. Temperatures remained high, rainfall was unpredictable, and ultraviolet radiation remained elevated. Soils, stripped of deep-rooted trees, eroded with every storm. Nutrient cycles faltered. Microbial and fungal activity dominated the breakdown of organic material, but the rebuilding of ecosystems, the growth of forests, the return of rich animal communities was hindered at every step. Some small vertebrates persisted. Decinodonts, particularly Lystrosaurus, became globally widespread, filling the barren landscapes. They were the last large herbivores of their time, capable of surviving in marginal habitats and tolerating extreme conditions. Small reptiles and amphibians survived in isolated refuges, but they were exceptions, not representative of a recovered ecosystem. This world, alive but barely, was both fragile and monotonous. Ecosystems lacked structure. Predator-prey interactions were minimal. Competition existed, but within a greatly diminished pool of species. The Great Dying had removed not just species, but the intricate balances and interactions that define complex life. Recovery did not happen in sudden bursts. It was measured in millions of years, fragmentary, incomplete. Forests eventually returned, but not for tens of millions of years. Reefs began to re-establish, but slowly in scattered locations. The fungal-dominated landscapes persisted long after the initial die-off, marking a prolonged liminal state in Earth's history. A world in which life existed, but the machinery of ecosystems, the complex, multi-layered interactions that sustain richness, was paused. That this was the abyss, a world stripped to its elemental survival, a world where evolution had slowed, ecosystems were simplified, and life persisted only because some organisms could endure extremes. The planet was alive, yet its pulse was faint, a whisper of what it had once been. And the question, heavy in the silence, lingers over this deadened Earth: why didn't life bounce back immediately? The world that emerged from the fungal-dominated landscapes of the early Triassic was not a world of renewal. It was a world of endurance. For millions of years, the planet remained in a state of near collapse. The processes that had once regulated temperature, oxygen levels, and nutrient cycling were broken. Oceans remained warm, stratified, and low in oxygen. Coastal waters, where life might have found refuge, were often acidic and sulfidic. On land, forests struggled to re-establish, their seedlings failing under intense heat, unpredictable rainfall, and ultraviolet radiation that had yet to fully recover. Every attempt at rebuilding ecosystems faltered. The fossil record of this time is stark. Layers of sediment reveal repeated die-offs, ephemeral blooms of opportunistic life, and long stretches of monotony. Plant communities never stabilized. Seed ferns and conifers reappeared in pockets only to vanish in the next ecological wave of stress. The so-called coal gap persisted, a geological record of plant scarcity. Forests, when they existed, were small, patchy, and low in diversity. The towering glossopterid forests of the Permian never returned. The land was largely open, barren, punctuated by the occasional hardy survivor. In the oceans, recovery was equally fitful. Early Triassic seas were dominated by small, opportunistic invertebrates, bivalves, gastropods, and certain brachiopods that could tolerate acidification and low oxygen. Reefs, once the bustling cities of the sea, were minimal, sparse, and fragile. Complex food webs were gone. Predatory fish were small and rare. Planktonic communities were impoverished, lacking the diversity that had driven marine productivity for hundreds of millions of years. Oxygen minimum zones persisted in deeper waters, creating long-lived refuges for anaerobic microbes, but leaving most larger life unable to colonize vast regions of the ocean floor. On land, vertebrates that survived the Great Dying became dominant almost by default. The most notable of these was Lystrosaurus, a small, stocky dicynodont synapside. With its tusks and beak, it could feed on tough, sparse vegetation that few other herbivores could exploit. It burrowed to avoid heat and radiation, and its global proliferation across Pangaea's southern continents marks one of the most remarkable examples of post-extinction success in Earth's history. Yet Lystrosaurus alone could not rebuild the ecosystems of the Permian. It was a survivor, not an architect of ecological complexity. Other small herbivorous reptiles and amphibians persisted in localized refugees. Some early archosauriforms, precursors to the dinosaurs, appeared but remained rare and small. Apex predators were largely absent. Without sufficient prey diversity and density, top-level predation was nearly impossible. Ecosystems were flattened, both literally and figuratively. The vertical complexity of canopy forests, mid-story shrubs, and ground-level plants had vanished, leaving only sparse, low vegetation. Repeated environmental stress ensured that life never gained a firm foothold. Volcanic activity in Siberia may have continued episodically, releasing CO2 and methane into the atmosphere. The oceans never fully mixed, oxygen remained low, and temperatures fluctuated widely. The planet was trapped in a feedback loop. Every attempt at ecological recovery was undermined by climate instability. Even small organisms faced challenges. Insects, which had survived the extinction in limited numbers, found few plants to feed upon. Reproductive success was low. Microbial mats and fungi dominated marginal habitats, reclaiming organic matter faster than it could support complex consumers. Seeds and spores that did germinate often failed due to drought, heat, or radiation. Evolution was slowed, not stopped. But its tempo was glacial by comparison to pre-extinction timescales. The pace of recovery, or rather the lack of it, is staggering. Estimates suggest it took 10 million years for ecosystems to approach anything resembling pre-extinction complexity. For perspective, the Permian forests and marine ecosystems had taken hundreds of millions of years to assemble. This was not a brief interruption, but a geological hiatus in life's elaboration. During this time, the survivors were few, resilient, and opportunistic. They were not innovative in the way life had once been. Small size, generalist diets, burrowing habits, and tolerance of heat and low oxygen became the defining traits of survival. Complexity was punished, simplicity endured. Food webs remained truncated. Predation was opportunistic rather than structured. Ecological interactions were fragile, and extinctions continued locally. This prolonged fragility meant that even the appearance of new life forms did not guarantee ecosystem stability. Small plant communities could flourish for decades, only to collapse under heat waves or drought. Amphibians could reproduce successfully in isolated wetlands, only to perish when water levels dropped. The planet remained a landscape of failed experiments. a laboratory in which evolution tested adaptation at the edge of possibility. It is in this context that the first true post-extinction innovations appeared. Archosauriforms began slowly to diversify, experimenting with upright posture and more efficient locomotion. Certain bivalves and gastropods adapted to increasingly acidic seas. Fungi evolved strategies to exploit dead plant matter more efficiently, but these innovations occurred in a world constrained by environmental stress. Nothing could establish dominance without enduring the same relentless pressures that had wiped out almost all other life. Even the climate itself resisted normalization. Polar regions, which had been temporary refuges for some organisms, warmed significantly. Equatorial heat remained extreme. The oceans, stratified and oxygen-poor, limited colonization. Global biogeochemical cycles, carbon, nitrogen, and phosphorus, remained disrupted. Nutrients did not circulate as they once had. Life had returned, but the planet had not. The survivors were a fragile bridge between the lost complexity of the Permian and the eventual rise of the Mesozoic biosphere. Lystrosaurus, microbial mats, opportunistic bivalves, and a handful of reptiles were the actors on a stage that had lost its sets. They persisted not because they were dominant, but because they could endure, tolerate, and reproduce under extreme conditions. Life's future would be built upon these survivors, but the memory of the ecosystems they replaced had been erased. This 10-million-year period of silence is a testament to the scale of the Permian-Triassic extinction. It was not just a die-off of species, it was a pause in evolution itself. Ecosystem engineering, niche partitioning, and complex food webs were absent. Life survived, but the processes that had once created diversity, resilience, and complexity had been interrupted. For millions of years, the planet existed in a fragile equilibrium, a liminal state in which survival was a daily struggle and innovation was painfully slow. In this prolonged aftermath, the question arises with stark clarity. What kind of life can survive a world like this? The answer is not grandeur, it is endurance. It is smallness, adaptability, and resilience. It is life that can persist through heat, low oxygen, radiation, and scarcity. It is not the bold apex predator or the towering forest, but the creatures that can burrow, reproduce quickly, and tolerate extremes. These are the architects of the next age, the lineage threads that will one day reweave the tapestry of life, but only after millions of years of planetary patience. The world that emerged from the shadow of the Great Dying was no place for grandeur. Forests were absent, reefs lay in ruins, and the air and seas remained harsh. In this harsh new reality, survival was no longer a contest of size or ferocity, but of endurance. It favored those who could withstand heat, low oxygen, toxic waters, and a planet that had become unpredictable. Into this void stepped Lystrosaurus, a small, stocky dicynodont synapsid, about the size of a modern pig with a squat, barrel-shaped body and sturdy limbs built for burrowing. It was unremarkable at first glance. It had neither the speed of a predator nor the elegance of a specialized herbivore. Yet in this world of extremes, it was almost indestructible. Across Pangaea's southern continents, fossils reveal Lystrosaurus everywhere: Antarctica, South Africa, India, and China. Species' global reach marks it as the most successful terrestrial survivor of the Permian-Triassic extinction. What made Lystrosaurus resilient was its simplicity combined with adaptability. Its beak and tusks allowed it to feed on tough, sparse vegetation that others could not digest. It could burrow, offering refuge from ultraviolet radiation, heat, and drought. Its reproductive strategy was flexible, allowing it to survive in unstable conditions where other species could not reliably reproduce. And while it was not fast or formidable, it did not require abundant resources, precisely the adaptation needed in a world stripped to its ecological skeleton. Lystrosaurus was not alone, but it was the defining survivor. Other small reptiles, amphibians, and opportunistic plants persisted, but none matched its dominance. In this early Triassic landscape, predator-prey dynamics were minimal. Apex predators were rare or absent. The ecosystems were flattened, functionally simplified. What existed were scattered populations of herbivorous survivors feeding on low shrubs, ferns, and occasional patches of seed ferns, with opportunistic predators lurking in the shadows. Across continents, Lystrosaurus became the foundation of terrestrial life. Its burrows created microhabitats for smaller animals, and its feeding patterns slowly reshaped the soil. By surviving in the most marginal environments, it kept the thread of life alive, providing a base upon which ecosystems could eventually reassemble, but only after millions of years. In many ways, Lystrosaurus embodied a principle far older than intelligence: resilience. It was not clever, social, or inventive. It had no hunting strategies to rival gorgonopsids, no flight or climbing skills to evade predators, no elaborate reproductive behaviors. Yet in a world where complexity had been punished, it thrived. The very qualities that might have seemed mundane in a stable Permian world, hardiness, adaptability, efficiency, became the keys to survival. This is the paradox of post-extinction life. Intelligence, elegance, and specialization, once advantageous, now became liabilities. Only those organisms capable of enduring extremes, of reproducing under scarcity, and of tolerating the relentless instability of the planet survived. Lystrosaurus was the embodiment of this principle. In doing so, it reshaped the evolutionary trajectory of the planet, setting the stage for a slow, uneven recovery that would eventually allow new forms, archosaurs, early dinosaurs, and later mammals, to rise. Yet even the reign of Lystrosaurus was not absolute or secure. Climate fluctuations continued. Oxygen levels remained low. Small-scale die-offs occurred repeatedly. The species' dominance was born of circumstance as much as adaptation. Its survival was testimony not to superiority in any conventional sense, but to the brutal arithmetic of endurance. By observing Lystrosaurus, we see what life rewards when the world is unforgiving. Survival is no longer about dominance in a competition of predators or cleverness in resource acquisition. It is about persistence in a collapsing system, the capacity to endure what others cannot, and the ability to exploit marginal niches that are inhospitable to all but the hardiest forms of life. And in this post-apocalyptic world, the question looms: is resilience more important than intelligence? The answer may lie not in the animals that survived, but in the millions of years of fragile ecosystems that followed. The world that emerged from the 10 million years of post-extinction silence was a planet both familiar and alien. Life persisted, but the rules had changed. Oxygen levels, still lower than before, constrained metabolism and growth. Heat and aridity dominated the interior of Pangaea, creating vast deserts and unstable river systems. Forests, when they appeared, were sparse, consisting of hardy ferns, lycophytes, and seed ferns that managed to eke out a living in soil stripped of nutrients. And yet in this barren, fragile world, evolution began to experiment again. The survivors of the Permian Triassic catastrophe were not simply relics. They were the architects of a new age. Among them, small archosauriform reptiles, the distant ancestors of the dinosaurs, began to diversify. In the shadow of Lystrosaurus and other dicynodonts, these early reptiles explored the empty niches left by extinct synapsids and amphibians. Unlike their predecessors, they were more agile, more efficient in locomotion, and capable of exploiting new ecological opportunities. Early archosaurs were small, generally lightly built, and primarily carnivorous. They thrived in the disturbed landscapes, preying on insects, small vertebrates, and scavenging where possible. Their evolutionary experimentation with upright posture, elongated limbs, and enhanced metabolism gave them an edge over the remaining sprawling reptiles. In the harsh conditions of the early Triassic, where resources were scarce and climate unstable, these traits allowed even small predators to survive and reproduce where larger, more specialized predators could not. As the Triassic progressed, these small archosaurs began to diversify into forms that would set the stage for true dinosaurian lineages. Some developed more erect postures, reducing energy expenditure while moving across hot, open landscapes. Others specialized in hunting, with adaptations in teeth, jaws, and limb mechanics that allowed them to exploit niches left vacant by the disappearance of gorgonopsids and other apex predators. This was a world in which flexibility and efficiency were rewarded far above size or brute strength. Meanwhile, the herbivorous side of terrestrial ecosystems remained dominated by dicynodonts, such as Lystrosaurus. These animals were slow to evolve in comparison to the nimble archosaurs, but their persistence allowed them to shape the environment. Their feeding patterns maintained vegetation at low levels, preventing any single plant lineage from dominating and creating open corridors across the landscape. In these open spaces, small archosaurs found ample opportunity to roam, hunt, and diversify. The selective pressures of predation, scarcity, and competition gradually sculpted them into the first recognizable proto-dinosaurs. By the mid-Triassic, roughly 20 to 30 million years after the Great Dying, the scene was set. The empty niches of the devastated world allowed archosaurs to radiate into new forms. Some became larger, bipedal predators. Others evolved into omnivores and small herbivores capable of exploiting new vegetation. This period of adaptive radiation was incremental, punctuated by repeated climate stress, but persistent. The slow pace of recovery meant that every evolutionary innovation was tested under extreme conditions: heat, drought, low oxygen, and sporadic food availability. Only the most resilient and adaptable traits survived. In the oceans, recovery mirrored the land in its sluggishness. Reefs reappeared in scattered patches composed not of complex corals but of hardy sponge-like organisms and small calcareous algae. Fish gradually diversified, but most remained small, avoiding the high metabolic demands of larger predators. Oxygen minimum zones persisted, restricting the distribution of complex marine life. Microbial mats dominated nutrient cycling, stabilizing shallow marine habitats and allowing limited invertebrate colonization. The shallow seas, though impoverished compared to Permian richness, provided corridors for dispersal of early marine reptiles and amphibians. Back on land, the climate created a patchwork of habitable refugees. Along river valleys and occasional lakes, ferns, horsetails, and conifers established small forests. These areas supported a limited herbivorous fauna, small synapsids, early archosauriforms, and newly emerging herbivorous reptiles. The availability of food in these microhabitats allowed selective pressures to favor early experimentation with size, locomotion, and diet among proto-dinosaurs. In contrast, the vast arid interiors of Pangaea remained nearly empty, a landscape dominated by heat, drought, and sand. These harsh regions acted as a crucible, testing the endurance and adaptability of every species that ventured into them. By the late Triassic, roughly 50 million years after the Permian-Triassic boundary, recognizable dinosaurs began to appear. Among the earliest were Eoraptor and Herrerasaurus in what is now South America. Small, bipedal, and predatory, these animals exemplified the combination of endurance, agility, and opportunism that had been rewarded in the post-extinction world. Their size allowed them to exploit resources that were unavailable to larger, slower organisms, and their metabolism allowed for sustained activity in warm, low-oxygen conditions. Herbivorous dinosaurs followed shortly thereafter, though their rise was gradual. Small, fast-moving forms grazed on ferns and low vegetation, often coexisting with Dicynodonts like Lystrosaurus. The balance of predator and prey began to re-establish, though ecosystems were still rudimentary compared to the Permian. Forests were low and sparse, and competition remained constrained by environmental instability. Yet in these corridors of life, evolution was experimenting once again with forms and strategies that would dominate the Mesozoic. What emerges from this sequence is clear. The Great Dying did not just wipe out life, it rewrote it. The extinction reset the evolutionary playing field. The collapse of synapsid dominance removed the pre-existing rulers of land ecosystems, creating opportunity for archosaurs. Climate instability, once a threat, became a selective filter, ensuring that only flexible, efficient, and resilient organisms persisted. The extinction had sculpted a world in which dinosaurs could emerge not by chance, but by virtue of the traits that allowed survival in the harsh post-extinction environment. In this reconstructed Earth, ecosystems remained fragile. The oceans and land were still recovering chemically and biologically. Oxygen remained lower than pre-extinction levels, imposing metabolic constraints. Extreme heat and seasonal drought shaped behavior and physiology. But within these constraints, dinosaurs and their immediate ancestors began to thrive, exploiting the empty ecological niches left by Lystrosaurus and other early survivors. By the end of the Triassic, the stage was set for the rise of true dinosaur dominance. Forests slowly expanded, allowing larger herbivorous forms to evolve. Predator-prey interactions intensified as carnivorous archosaurs increased in size and efficiency. The planet had emerged from a period of near-total collapse into a landscape of opportunity, shaped by the extinction event that had reduced life to a handful of survivors. In other words, the extinction had not just removed species, it had rewritten the rules of Earth's future. Across Pangaea, the interplay of survivor species, environmental constraints, and empty niches created a feedback loop that favored dinosaurs. Traits that had previously been secondary, upright gait, metabolic efficiency, rapid reproduction, small size under stress, became the foundation of evolutionary success. Dinosaurs were not inevitable in a pre-extinction world. They became inevitable because the world had been restructured by catastrophe. In essence, the Permian-Triassic extinction acted as a planetary editor, erasing complexity where it had once flourished and leaving blank spaces for life to fill anew. Dinosaurs emerged not because they were inherently superior, but because they embodied the traits that allowed life to persist in a world scarred by apocalypse. The sequence of emergence, small, agile archosaurs first, followed by more specialized carnivores and herbivores, reflects the slow rebuilding of ecosystems constrained by temperature, oxygen, and resource availability. And in this reborn world, we see the echoes of the Great Dying everywhere. The deserts and river valleys, the fragmented forests, the sparse oceans, and the patchy food webs all bear the signature of a planet still haunted by extinction. Dinosaurs would rise to dominate, but they did so on a canvas painted by catastrophe. shaped by survival under conditions that favored endurance over elegance, flexibility over strength, and opportunity over dominance. By the end of this long resurrection, one truth becomes evident. Extinction did not simply remove the old, it created the new. The blank landscapes, the fragile refuges, and the survivors' adaptations did more than preserve life. They defined the trajectory of the Mesozoic. Dinosaurs were possible because the world had been emptied, reorganized, and tested. The Great Dying, in its cruelty, became the architect of a new Earth. And the question remains, lingering across the deserts and river valleys, in the shadowed oceans and scattered forests. Did extinction secretly rewrite Earth's future? The answer, written in stone, fossil, and the bones of the first dinosaurs, is unmistakable. Yes, it did. The Permian world speaks across the gulf of time. It is not a whisper, but a roar, a cautionary tale that demands attention. The continents, oceans, and skies of 252 million years ago may seem alien, but the forces that ended that world are not gone. They persist in echoes, refracted through the lens of our own era. The Great Dying was not caused by an asteroid, nor by a sudden cosmic event. It was a crisis born of the planet itself, a planetary scale imbalance triggered by greenhouse gases, warming oceans, and the collapse of chemical and biological feedbacks. Today, we are experimenting with the same variables, albeit on a human timescale. The parallels begin with carbon. In the Permian, the Siberian traps erupted, pouring trillions of tons of CO2 into the atmosphere over tens of thousands of years. The result was a greenhouse warming unlike anything the biosphere had experienced. Polar regions warmed dramatically. Oceans absorbed the heat and acidified. Methane hydrates destabilized, releasing more greenhouse gases. Life, which had evolved under a delicate equilibrium of oxygen, carbon dioxide, and temperature, could not adapt fast enough. It collapsed. Today, we pump CO2 into the atmosphere at rates that would have shocked even the most extreme Permian volcanism. Fossil fuels, land use changes, deforestation, all of these are injecting carbon at a pace measured in centuries rather than millennia. The oceans absorb a portion, acidifying along the way. Ice melts, sea levels rise, and climate zones shift. The parallels are not perfect. Human intelligence is present, a factor that distinguishes us. But the underlying physics remain unchanged. The Earth's atmosphere responds to greenhouse forcing the same way it did 252 million years ago. Consider temperature. During the Permian, global averages climbed by as much as 10 degrees Celsius in some models, but polar regions saw increases far greater. Tropical waters became lethal, reefs bleached. Oxygen concentrations plummeted in the oceans, creating dead zones across continental shelves. Terrestrial life faced heat waves that surpassed the tolerance of even the hardiest animals. We see the same trends today. Ocean heat waves are increasing, coral bleaching events are more frequent, and extreme temperatures are becoming common. Oxygen-depleted zones in the oceans are expanding, threatening the collapse of fisheries that billions rely upon. Yet the most uncomfortable parallel is not climate itself, but the fragility of life in the face of systemic stress. The Permian extinction unfolded in phases, cascading through oceans and lands, top predators and primary producers alike. It was not a single event, but a chain reaction. Greenhouse warming triggered ocean acidification, which triggered methane release, which accelerated heating, which collapsed the ozone layer. Terrestrial forests burned or died standing, soils eroded, and the simple act of survival became nearly impossible. Humans, like Lystrosaurus or the tiny archosaurs that later became dinosaurs, are part of this planetary system. Our civilization depends on the stability of oceans, the predictability of climate, and the productivity of ecosystems. When the system is pushed beyond its threshold, the consequences are indiscriminate. We like to imagine that technology, governance, and foresight will protect us. Perhaps they will. Perhaps they will not. The Permian reminds us that life's complexity, no matter how advanced, is vulnerable to overwhelming environmental shifts. Intelligence does not confer immunity. In fact, it may create blind spots. The more we depend on engineered systems, monocultures, and globalized networks, the more exposed we become to cascading failures. A single variable, carbon, temperature, oxygen, can propagate disruption in ways that are hard to foresee. History also teaches us humility. During the Permian, no species was exempt. Apex predators, small burrowers, marine filter feeders, and giant herbivores alike fell victim to environmental collapse. Even species that survived for millions of years, adapted to ice ages, volcanic eruptions, and continental drift, could not escape the combined force of runaway greenhouse warming, acid oceans, and atmospheric collapse. Humans, despite our intelligence and technology, are not fundamentally different. Our ingenuity is a tool, not a shield. and it may not suffice if planetary systems themselves fail. The sequence of events is instructive. Carbon accumulation first raised global temperatures. Oceans absorbed the heat and acidified, killing coral and invertebrates. Methane hydrates destabilized, adding fuel to the warming. Forests collapsed. Ultraviolet radiation reached the surface as the ozone layer thinned. Species went extinct in waves, often regionally at first, then globally. Feedback loops magnified each step. The lesson is clear. In a tightly coupled system, small imbalances can become catastrophic when thresholds are crossed. Today, our emissions, deforestation, and industrial activity are nudging the same global feedbacks. Ice melt accelerates warming. Heat kills plankton, reducing carbon uptake. Ocean currents slow or shift. Methane escapes from thawing permafrost. The chain reactions may be slower than the Permian volcanic pulse, but the trajectory is comparable. We should also consider time. The Permian extinction did not end life. Microbes, fungi, small reptiles, and dicynodonts survived. The planet recovered, eventually giving rise to the age of dinosaurs. But recovery was measured in millions of years, 10 million for ecosystems to regain complexity, 20 million for forests and reefs to stabilize. Humans often talk in decades and centuries, but Earth operates on a far slower clock. Even a small disruption can reverberate across millennia. The fragility of recovery is as instructive as the immediacy of collapse. And yet, there is a paradox. Life is resilient. Lystrosaurus survived because it was small, hardy, and adaptable. Early archosaurs survived and eventually gave rise to dinosaurs. Microbes flourished, recomposing the chemical and biological framework of oceans and soils. Extinction is brutal, but it does not erase potential. There's hope in the survivors, but hope requires understanding the constraints imposed by the environment. Resilience emerges not from intelligence alone, but from traits aligned with the world as it exists, not as we wish it to be. The human parallel is stark. We have unprecedented capacity to adapt, to alter environments, to engineer refugees. Yet we are also imposing stresses faster than the planet has ever experienced. Climate models suggest that continued emissions could push global temperatures and sea levels toward thresholds that, while not identical to the Permian, would challenge the survival of countless species, including ourselves. Coral reefs, fisheries, tropical forests, and even agricultural systems may experience collapse in decades rather than millennia. Feedback loops, methane release, ice albedo changes, ocean deoxygenation mirror the Permian sequence in alarming ways. The lesson of the Permian is not inevitability but awareness. Catastrophe was not a random strike. It was the product of interacting forces operating beyond the thresholds of life. The survivors were not the strongest in a conventional sense, but the most adaptable, resilient, and capable of persisting under extremes. Intelligence mattered little when fundamental environmental systems failed. In the modern context, this is a warning. Our ingenuity must align with planetary constraints, not override them. Otherwise, we risk a chain reaction of collapse unlike anything human history has encountered. Even as we reflect, Earth continues to move along its own trajectory. Oceans absorb heat, atmospheric carbon rises, and ice melts. Species migrate, adapt, or perish. Forests die, reefs bleach, and ecosystems shift. The speed and scale are unprecedented in the last 66 million years, and we are the agents of change. The Permian is no longer distant history. It is a mirror, reflecting what can happen when the planet's feedbacks are pushed too far, too fast. The uncomfortable truth is this: the world survived the Great Dying not because extinction spared some species, but because resilience found a foothold in extreme conditions. Lystrosaurus endured, early archosaurs endured, microbial life endured, the planet itself endured. Humanity, with all its tools and ingenuity, is no exception to these laws. The question is whether we can learn from the Permian, whether we can recognize thresholds, slow feedback loops, and the interdependence of every system, from atmosphere to ocean, from soil to forest. And yet, as with the survivors of the Great Dying, the opportunity is profound. The planet is not static. Ecosystems can recover if we align our actions with environmental constraints. Carbon can be sequestered, forests can regrow, oceans can stabilize. Unlike the Permian, humans have the awareness and tools to anticipate tipping points rather than endure them blindly. But the window is narrow, the stakes high, and the clock relentless. The Permian-Triassic extinction challenges more than our understanding of paleontology. It challenges our hubris, our assumption of permanence, and our belief that intelligence alone can insulate us from planetary forces. It reminds us that life, no matter how abundant or sophisticated, is contingent upon thresholds, feedbacks, and the subtle balance of global systems. And it forces a reflection. If the greatest extinction in Earth's history can occur without an asteroid, without a cosmic trigger, without warning, what guarantees do we have today? For the modern observer, the lesson is uncomfortably clear. The Earth will continue with or without us. Its chemical and physical laws are indifferent to ambition, morality, or civilization. Human activity can either nudge the planet toward stability or push it toward instability. The line is thinner than we often admit. Just as the oceans and continents of the Permian crossed invisible thresholds that triggered collapse, so too can our current Earth system respond to accumulating stress with sudden cascading consequences. The shadow of the great dying lingers not in fossils alone, but in the patterns of planetary dynamics. It is a cautionary whisper in rising CO2, in acidifying seas, in polar ice loss, in extreme weather events, and in the fragility of ecosystems. And yet, it also offers a measure of hope. Life endured then, and life can endure again, but only if we understand the rules, respect thresholds, and act with foresight. The question, unflinching and stark, stretches across the aeons. What lessons from 252 million years ago can guide a species capable of shaping the climate, altering oceans, and influencing the survival of countless others? In the echo of the Permian, the answer is neither simple nor comforting. The planet is indifferent. Survival is contingent, fragile, and defined by resilience as much as intelligence. And the next great challenge, if ignored, may not come from space, but from the very atmosphere, oceans, and soils that sustain life. We began this journey in a world that seemed unshakable. Vast forests, thriving oceans, and towering predators created the illusion of permanence. The Permian Earth appeared eternal, its complexity and abundance a guarantee against collapse. Yet, in a few tens of thousands of years, almost all of it vanished. 96% of marine species, 70% of land vertebrates, forests stripped bare, oceans poisoned, the skies darkened with ultraviolet radiation. Life's triumphs were erased in a geological heartbeat. And still the Earth endured. Life found footholds where it could, tiny survivors navigating an alien landscape of heat, toxicity, and scarcity. Lystrosaurus burrowed, fungi carpeted the land, microbes dominated the oceans. Evolution slowed, but it did not stop. Ecosystems rebuilt, painfully, imperfectly, slowly, over millions of years. The world emerged, altered, transformed, and prepared for the next age, the age of dinosaurs. The lesson is both simple and profound. Catastrophe does not discriminate. Intelligence, size, beauty, or strength, these are irrelevant when the foundations of life itself are destabilized. Only those who can endure extremes, tolerate scarcity, and persist across uncertainty survive. In the aftermath of collapse, it is resilience, not dominance, that defines the trajectory of life. And yet, the story of the Permian is not merely one of extinction and survival. It is a cautionary tale about thresholds. Life can absorb shock, but only to a point. The Siberian traps did not collapse Earth by accident. They pushed atmospheric carbon, ocean chemistry, and temperature beyond thresholds that complex life could tolerate. Once those invisible lines were crossed, feedbacks cascaded unchecked. Methane released from seafloor hydrates, oceans acidified, ozone thinned, forests collapsed. Life, evolved over hundreds of millions of years, could not keep pace. We cannot dismiss these patterns as relics of a distant past. The mechanisms that drove the Permian extinction remain intrinsic to the planet. Carbon cycles, greenhouse feedbacks, ocean chemistry, atmospheric dynamics. Humanity now has the capacity to influence these systems, to alter them faster than natural processes ever did. The question is whether our foresight will be enough to avoid repeating history. Are we resilient enough individually and collectively to withstand the pressures we have unleashed? The answer is not assured. Like the early Triassic, our world may already be in a precarious state. Global temperatures are rising, oceans are warming and acidifying, ice caps are melting, and extreme weather events are intensifying. Feedback loops that took millennia to manifest in the Permian may unfold within decades today. And yet, unlike the Permian biosphere, we possess intelligence, technology, and an awareness of the consequences of our actions. Unlike the Permian creatures, we can anticipate thresholds, study feedbacks, and take corrective action. Our resilience is not inherent. It must be chosen, cultivated, and applied on a planetary scale. The survivors of the great dying teach us another lesson. Adaptation is often modest, incremental, and unglamorous. Lystrosaurus was not elegant. It did not dominate through intelligence or ferocity. Its advantage lay in endurance, simplicity, and opportunism. Early archosaurs were not remarkable predators at first. They became formidable only through iterative adaptation in a world stripped of competition. Evolution rewards persistence, not brilliance, when the rules of survival are rewritten by catastrophe. Yet even persistence has limits. The Permian extinction unfolded in stages, with initial survivors facing repeated waves of environmental stress. Recovery was not linear, not guaranteed. Ecosystems collapsed multiple times in the aftermath. Forests and reefs failed to re-establish for millions of years, and evolution itself slowed. Life is resilient, but it is not invincible. The longer the stress persists, the more fragile even the survivors become. In observing the Permian world, we also see the profound consequences of interconnectedness. One system fails and others follow. Carbon dioxide levels rise, triggering ocean acidification, which disrupts plankton, which collapses food webs, which destabilizes the atmosphere further. Heat triggers methane release, reinforcing warming. Forest die-offs alter soils, reducing carbon storage. The sequence is not linear. It is a network of feedbacks, a planetary web where perturbations amplify one another. Today, our industrial and technological networks are also tightly coupled. Disruption in one domain, climate, energy, or food systems, can cascade across others. The lesson is clear: resilience requires understanding interconnection, not just isolated strength. But there is hope embedded in this history. Life endured, and so can intelligent action. The post-Permian world, though impoverished and fragile, eventually gave rise to the dinosaurs, then mammals, and eventually humanity. Recovery is possible, but it requires time, patience, and the capacity to navigate instability. The Permian is not merely a warning, it is a blueprint for endurance. It demonstrates that survival depends on flexibility, foresight, and the ability to exploit opportunities while respecting constraints. We are the first species in Earth's history capable of intentionally influencing global systems with precision. Unlike Lystrosaurus, our resilience depends not on passive adaptation but on deliberate intervention. We can reduce greenhouse emissions, stabilize ecosystems, restore forests, and manage oceans. We can, if we choose, align human activity with planetary thresholds instead of ignoring them. In this, intelligence becomes a form of resilience, but only if applied wisely. The final lesson is existential. The Permian extinction is a mirror reflecting the fragility of complex life. It is a reminder that abundance, stability, and dominance are temporary. The world can change faster than we imagine, and even the most successful species can be swept aside. It challenges us to reconcile ambition with humility, power with responsibility, and knowledge with foresight. Survival is neither guaranteed nor permanent. It is contingent upon alignment with the forces that govern the living planet. As we look to the present, we face a choice. We can continue to ignore the feedbacks, accelerate change, and assume that human ingenuity alone will shield us from planetary thresholds. Or we can act with the awareness that the Earth's systems operate on scales far greater than individual lifetimes, and that resilience must be engineered, nurtured, and respected. The story of the Permian is not a relic, it is a compass. It points to the consequences of overstepping limits and the opportunities inherent in adaptation. Ultimately, the question posed by the stones, the oceans, the empty forests of the Triassic, and the fossilized skeletons of Lystrosaurus is timeless. Can life endure when the rules change? The Permian tells us that endurance is possible, but only for those who respect the thresholds of survival. Intelligence alone is not enough. Resilience, adaptability, and understanding of systemic limits are what determine whether life continues or collapses. The Earth did not intend for the Permian extinction to happen. It occurred because thresholds were crossed, feedbacks cascaded, and life, complex, abundant, and confident, could not keep pace. The survivors endured, and through them life continued. Dinosaurs rose, mammals persisted in the shadows, and eventually humanity appeared. But the lesson is enduring. The planet is indifferent, and survival is not guaranteed. As we emerge from this reflection, the Permian continues to speak, not as a distant event, but as a living caution. Its echoes remind us of our vulnerability, our potential, and the responsibilities of intelligence. We inherit not just a planet of abundance, but a planet of thresholds, feedbacks, and consequences. What we do now will shape whether the future resembles the thriving Triassic ecosystems or the fungal, barren landscapes that followed the Great Dying. The stones, the oceans, the skies, they ask nothing of us in words. They do not demand belief or allegiance. They demand attention, calculation, and respect. The Permian Triassic extinction whispers a truth that resonates across time. Life is fragile, ecosystems are delicate, and the planet's capacity for recovery is measured in millions of years. Human survival is contingent upon recognizing limits, aligning actions with planetary thresholds, and cultivating resilience on a scale that matches the magnitude of the forces we have unleashed. And in that silence, in the shadow of the greatest extinction in Earth's history, we are left with the final question, unflinching, persistent, and unresolved. If life could survive the collapse of an entire world once, can it survive the choices of its most intelligent species today? If this journey through our past helped you understand what it takes to survive, subscribe to Science of Survival. We release new documentaries every week, exploring extinction, adaptation, and the fragile line that keeps humanity alive.